Hi, I'm Guo Cheng Guang, second year one for NS High School. In this lesson that we have over here is electromagnetic dynamics. Well, in the last lesson of electromagnetic dynamics, we had a question about, well, you can say a rod above x-axis, and the length of this rod that you have over here is L, and the total charge of that rod or the wire is Q. Then you have a point P on the x-axis and its charge is negative Q. Then from this rod, we have to find the total electrostatic field strength on this P point. So from this rod here, we had EX in that direction, and EX is found here. And then we also had EY, which is also the Y component, which is going down. Then after that, we found the total electrostatic field strength, which is here around this direction. So when we change this part a little bit, so how we change it, above here, at first we have a rod, then let's extend the rod. Well, you can say we double the rod, then the other part is below the x-axis. Then let's take a look at this part below, what happens. So length, charge, they're all the same. So you also have the x component in that direction for this little rod here. Okay, x component. Then the y component will be upwards. So, wait, let me just draw that out. So for this part, the new part will be here will be for your y component. Then for the original part, you had one going down. And for both of them, they have EX. And EX is actually just on this x-axis that you have over here. So that means in total, EY, so the one above, which is going down, and the one below that's going up, they'll cancel each other out since they have the same value for both. And then for the part of the x component, since both are in the same direction and same value, that means they're just double. So the total EX for this part will become, so total EX. So just times 2. Then afterwards, how about let's change this Q a little bit. Since this Q, you're saying about the total charge that you have, we can change it into the linear charge density. Then since it is uniformly distributed for the charge, that means the eta, which is the linear charge density, time is the constant, then you can times L. So we can change it into this form here. So that means these two parts, we don't have it anymore. Okay, next. Other than this part that we will have, so from here, okay, according to here, that means we'll have a 2 pi epsilon naught in this denominator here. So then for this length that we have, what if we have infinite length? So that means L it approach to infinity. So then limit L approaches to infinity. Eta times L over 2 pi epsilon naught x square root x squared plus L squared. Then from our limit here, we can divide L on both sides. So in the numerator, you have eta, then below 2 pi epsilon naught x, then square root x over L square, they add 1. So from this part, since L is approaches to infinity, this part, this square here, will be a 0, so then square root of 1 is still 1. So that means what you get will be eta over 2 pi epsilon naught x. So this will be the first part of the EX that we will get. Right. So then right now here, I'm going to use another way to find this. So for this other way, since this length here is infinity, wait, I may need to use this space here. So since I've already recorded it down, I'm just going to erase this part. But I'm just going to add on a little bit more. Since EX for this whole part, the only thing that we have is in the X direction. So actually for this part, the EX is our E. Since you only have it in the X direction, so they are the same. Then, although we have already found this, I'm going to use another method to find it. And this method, we have learned a little bit of it before. As we are using the Gaussian law. You can say Gaussian law, you can say Gaussian theorem, Gauss law, Gauss theorem. There are different ways to say it. So for this Gaussian law here, you're just going to have, well, this A you can also write it as an S if you want. So this is the Gaussian law. Well, let me explain a little bit more about this Gaussian law that we'll have. So in this part of Gaussian law, when we look at the different parts of it, first of all, here it looks like double integration, or you can call it like surface integration for this part in front. Then E vector, this is a dot dA vector. This part inside here we're using dot product. So E in this part is electrostatic field strength. Then dA, well, we can say like it's just in a normal direction for this part here. So that means when they're dots together, this part you can just call it the flux. Then that means flux being equal to, so 1 over epsilon naught sigma. Well, sigma, that means you add up all of the charges. So that means it's just a relationship between the flux and the charge. But wait, it may sound very, very simple, but you have to be, well, where is it? Well, when can we use it? And many things like that. Alright, for example, this flux over here. Flux of what? This is the flux of electrostatic field strength. And where is this flux? This is only on the Gaussian surface that you have chosen. So this flux for electrostatic field strength is on and go through the Gaussian surface. Then for the other side here, which is the charge. So charge inside the Gaussian surface. This is the other part. So in all, it can become very long, which is the relationship between the flux of electrostatic field strength on the Gaussian surface, and in fact goes through the Gaussian surface, and the total charge number, and the total charge inside or within the Gaussian surface. So it is a relationship between simply just flux and charge. Well, it depends on like which type of Gaussian surface you choose, because for different cases you may want to choose different Gaussian surface. Like it depends on what you are using for this Gaussian surface, and so it may affect the whole Gaussian law. And one limitation to this Gaussian law is that you can only use it for special cases. Okay, so you have to be aware of that. Only some cases you can use Gaussian law. There are actually many cases whereas you cannot use this Gaussian law here. Well, in this case, let me just tell you, we can actually use it. So I'm going to draw this part out. So first of all, as we're taking this length of this thing, or this wire, to be infinity. So you could just draw a straight line down. And you can see this is a wire that we have for this part. Well, from this wire, what do we want? So we can have the equal distance to each of the points. So to each of the points on the Gaussian surface. So that means we can use like, for example, these 2 points that I can also mark out. Some more. Okay, then wait, I also have to draw that this is actually the radius. Just to show that they are the same. So this part and this part. This part and this part. Or both of these, they are equal. Okay? So then these are the 4 points that I marked out. You can also mark out more points like inside. You can also go down some more. You can also go up even more. Since this line or this wire is of length infinity, so you can draw as many as you want. You can draw for days, nights, but still they're the same thing. So in this part that we'll have, this wire is charged, alright. So this wire is charged, we need to find in which direction would this electrostatic field strength be. So since this is on the inside, okay, this is on the inside, that means they'll go out in this direction, alright? But when you draw these parts, this is E, they have to be of equal length. Well, you may ask, why must it be of equal length? Let me just tell you. So in this part, since I've made these equal distance, and it is from the same charged wire or charged object, you can call it. Same distance, same charged object, so they're definitely the same. And in fact, it's of length infinity. Okay? Alright, so let's just say we have these 4 points, and this will be the direction of the electrostatic field strength that's acting on them. So then we can choose to connect them together to show that in this whole part, yes, you all have it like that. So in this whole part here, they're all facing outwards. There. And you can draw a lot more. So then from this part, since we want equal distance from each of them, that means this would just become, because equal distance, then there will be all circles. They're just stacking circles on top of each other. So a lot of these circles stacked up, you'll get cylinders. Alright, so this will be the Gaussian surface that you have. So we have already solved one problem, which is our Gaussian surface. Which shape should we use? Alright, so we have solved that problem here. Then after that, how many surfaces do we have? Since we need to find for each of these surfaces. So on top here, a circle, we have S1. Below, okay, another circle, S2. Then how about this curved surface here? It is also a surface S3. Well, just take note that there's only one surface here. So that means we have 3 surfaces in total. And so for this part, we can just separate them into their respective surfaces. Now, let's take a look at each of these surfaces. What will they give us? Firstly, S1. So S1, that means they're all in this either, okay, so you can just call them like outward direction or radial direction for this part. So, okay, E, direction of the electrostatic field strength, we have already found it. They're all just outward, radial direction, this part. How about the direction for dA? So it is on this surface, that means we're just like finding the normal direction, which will be upwards. And in fact, this applies to every single point. Okay, or I should make it a little bit shorter here. So this is what we'll have for every single point. Every single point, they'll have E outward, while for dA will be upward. Okay, like for example, I say this point here, you have dA upward. Then from these points, E outward, well, that means they're actually perpendicular to each other. Since this E, well, you can say it's on the same surface as the circle, but dA is perpendicular to this circle, or perpendicular to this surface here. So, yeah, they are perpendicular. They are perpendicular after this dot, which will have a cosine 90 degrees. Cosine 90 degrees, so there will be 0. So the first part you get is 0. Then let's see what's next. The next part is second surface, which is down here, this circle here. Okay, firstly, the direction of E. So the direction of E still for every single point, what you have will be an outward direction. Like this. So for this part here, so this will be what happened for their E, which is the electrostatic field strength. Then for dA, which will be their normal direction, you can actually say whether is it inward or outward. So let's just say that here we take it as an outward direction. Then let's say it's just still the same point. Then this will be going down. I can also draw a little bit shorter if you want. So then, for this part, just by looking at this point, you can find that it is perpendicular. Or just you have to think in 3D. You cannot just go and take a protractor and measure this part. You cannot do that. So from this part, this thing applies to every single point. That means for every single point, they'll have this perpendicular angle here. So that means you still get cosine 90 degrees. And after the dot, you get 0 again. Okay. So that means the first surface, the second surface, they're all 0 already. Then how about the third surface here? The third surface here, E, okay, we have already found that they are going outward or radial direction. Then how about for the dA vector here? That means we're finding for the normal direction. Let's just say we take this point here. So in this direction is the E. Then for dA vector, normal direction, which means it's still the same direction. So it's still in the same direction, get cosine 0, and it applies to every point. You will every single point, okay? So it is the same direction, cosine 0, which is 1. So then you just get EDA, alright? So then for EDA, can we make any more other changes to it? Let's take a look at E. We'll take a look at E first. So E, well, we know that every single distance is the same, and in fact they have this infinitely long, and actually this means E is the same for every single one, since we know that the length to this object here is the same, and it's infinitely long, the y they all cancel out, and so they all have the same. So E becomes a constant. Well, E is a constant in this case, not like for every single example you just put E is constant. You will, in this example, yes, E is a constant. Then you just have double integration dA for surface 3. So that means it's just like the circumference of circle, they just times the height. Well, the height, what you could take it as is an h. So circumference you just take as 2 pi r. Then the height just take as h. Alright, so this is what you get for this first part. So then after that, we have already found in the first part, so E 2 pi r h. Then how about this part behind here? 1 over epsilon naught, okay, that's a constant. 1 over epsilon naught. Total charge, well, total charge for this thing. So that means you need the linear charge density, which we'll use eta here. Then you have to times. So the total length of it. So the total length here we use is L for this part here. But in this example here, we have used H. So yeah, we have to be where L is in this, well, H is for this part that we have used here. So H, both sides they will cancel out. Then E will be eta over 2 pi epsilon naught r. Then we compare to what we have gotten before here. So eta still the same, 2 pi epsilon naught r and x. Well, because here what we have used, we use this part as an x. Well, in this Gaussian surface here, we have used x as the r. So that was what we have used in this case here. Okay, so here is we used x, here we used r. Well, they can just be like at this point, then they may be somewhere around at this line here. For example, it may be here. So this will be what we have in this lesson here. So in this lesson, we have used, well, first part is just to find EX using what we have found before. The second part here, we're just using Gaussian law, but beware, Gaussian law only for some special cases only. Okay, so that'll be all in this case, or in this lesson here. So if you like our videos, don't forget to subscribe to our channel. We'll see you in the next lesson. Thank you for your watching.